listeners of the Bio Report, I want to tell you about a new member benefit from the California Technology Council. CTC has teamed with Reprivada to offer members 6 months of Reprivada's COT network service for free, which gives companies the power of a VPN at a fraction of the cost. A remote, flexible workforce is the new normal, but most corporate networks aren't built to accommodate work from home at scale. Reprivada's COT network offers an easily deployable, affordable, and scalable solution to securely enable remote workers and protect the corporate network. To learn more about this and other member benefits, go to californiatechnology.org/member benefits. I'm Daniel Levine, and this is the Bio Report. Alvarez, a West Point graduate who earned a Ph.D. in bioengineering from MIT, served 20 years in the military, including time as an intelligence officer in Iraq. He saw injured soldiers who doctors were able to save, only to later have their limbs amputated because of the inability for injuries to heal properly. The experience led him to develop a means of turning recombinant proteins into a form that allows them to be used as coatings that act like paint and can be applied to implants to promote growth and other benefits. We spoke to Alvarez, founder of Theradaptive, about his journey from the battlefield to the lab, how his company's platform technology works, and the range of applications to which it may be applied. Lou, thanks for joining us.
It's great to be here, Dan.
We're going to talk about regenerative medicine, Theradaptive, and your efforts to improve the ability of bones to heal. I'd like to start with your own journey and how you became involved in the field of regenerative medicine. You're a West Point graduate, and you have a master's in chemical engineering and a Ph.D. in biological engineering from MIT. You've also got 20 years of active military service and earned both a Combat Action Badge and a Bronze Star Medal. How did you come to West Point? When did your interest in science begin?
It's an interesting trajectory, not one I would necessarily recommend to others pursuing a career in science, but it's been quite a ride nonetheless. But so my interest really started early in school. And I always knew I wanted to devote my life to science. But about around the time that I was graduating high school, I got an itch to prove myself physically and maybe militarily. So I decided to go to West Point. And West Point provided a very good foundation for my further studies later on in science. Had the rigor and kind of engineering focus. West Point being an engineering school originally and still is. So it provided a good backdrop for me to then continue my studies after finishing at West Point.
Your military service included time in Iraq. How much of your time was in an active military zone?
Right. So after finishing West Point, I actually was lucky enough to receive a Hertz Foundation fellowship, and it's a foundation that pays for graduate school in the sciences. And that allowed me to remain on active duty, but to pursue graduate school. And then after that, 2 years, then I was reassigned to units, more traditional, tactical Army units. And that included time in both the U.S. and, as you said, in Iraq. So I deployed with the 1st Cavalry Division to Iraq as an intelligence officer. And that tour was a little over a year, but that period of time between the master's and the PhD was about a 5-year period of time.
What was your experience in Iraq?
So it was actually in Iraq that I think this idea crystallized in my mind, what it is that I want to do in science. A lot of young people come in to a scientific field and maybe have a question about what direction to take. Really, there's so many options. But what I saw there and what I almost nearly experienced myself several times, these injuries that lead to lifelong, disability. Several of the people I was serving with had injuries, for example, to the limbs, lower limbs. When they got back to the States, medical science was able to save their lives, but some of them suffered amputation and now have lifelong disability. And all that was due to the fact that there really wasn't anything out there to regenerate tissue. So that idea is what motivated me when I got back from Iraq to go back to MIT again under a Hertz Fellowship to do a PhD and to focus on this idea of precise tissue regeneration.
And how much contact had you had with people who became amputees?
Well, after I got back, I did have a lot of more interactions with folks in the Bethesda region near the Walter Reed Military Medical Hospital and just others that I had served with who had suffered various injuries. So it was a period of time, 2005, 6, 7, and 8, where there were various surges, and so more and more people that I had served with or people that they knew were suffering injuries. So it's a close knit community. You end up seeing many of them again.
You returned to MIT to earn a PhD in biological engineering. What was the work you did there? How did it connect?
Sure. So when I went back, the Army gives you 3 years basically to do a PhD. So I knew I had to hit the ground running and have a plan for what to do. And MIT's Department of Biological Engineering was very welcoming and said, pick the professor that you want to work with. So I worked with Linda Griffith, who was really a pioneer in the field of regenerative medicine and tissue engineering. Actually, she was a postdoc in Bob Langer's lab, who developed the ear on the back of the mouse back in the 90s. So, real rich tradition of tissue engineering there. And it was in her group that I was able to focus on this idea of targeted delivery of proteins to induce the body to regenerate tissue.
Was it well understood why these soldiers who would come home would have their lives saved, but then end up losing limbs?
Yeah, it's a great question, and it's something that maybe doesn't get a lot of attention. So, if you injure a limb, normally that injury affects bone, it can affect nerves and the vessels. If any one of those tissues doesn't heal properly, then you end up with a limb that isn't usable. It actually becomes a burden to you. And medical guidance is that what's recommended is amputation, which is amazing to me that you would basically discard a limb because one of the wires is not healed correctly, so to speak. So to me, I wanted to address the problem on a very detailed level to say, can we regenerate, let's say, bone? So now you can save a limb if the problem is that the bone isn't healing. So it's a piecewise approach to trying to salvage limbs.
What are bone void fillers and how are they used today to repair fractures?
So today there are many products that, as the name implies, there's a hole or a void that needs to be filled. And these products actually provide just a framework for the body's own cells to crawl into and throughout that filler and make new bone. And it's a very important class of products, but really the current state of the art doesn't do anything more than just give a scaffolding, if you will. It doesn't induce the body to actually produce bone. And so the technology that the Theradaptive is developing is actually one in which it turns that scaffold into an instruction for the body to make new bone.
As I understand it, these are generally ceramic structures. Does the body today do something to incorporate or fuse to them?
Yes, it's interesting. Ceramic materials are actually quite good because when new bone is forming, the body actually produces an acidic environment where the injury is. And those acidic environments dissolve the ceramic and give the bone the calcium and the phosphates that are required to make new bone. So it's even though it's a very old world material, ceramics actually are a good starting material to make new bone because of what they're composed of.
Theradaptive is working to develop and commercialize recombinant proteins that can coat implants and devices like paint and promote growth. You've developed a computational platform to generate these. What has been done to identify a candidate protein and convert it into a material that can be used as a coating?
Yeah, it's a great question. So one of the great discoveries that was made in the early days of tissue engineering is that certain proteins, when placed in the body, can induce and force the body to make a specific kind of tissue. And one important protein called BMP2 actually forces the body to form bone. And one of the challenges, though, is that proteins don't like to stay where you put them. They like to diffuse away. And this has many problems. You'll form bone and the surrounding tissue where it can become actually more devastating. So the technology that the Theradaptive has developed is basically one in which you can now modify the protein, and that modified version will stick almost like a paint to the ceramic implant. And so now a surgeon can use this approach with this type of implant and have confidence that the protein isn't going to diffuse away. It's going to stay exactly where you want it. And what that lets you do now is say, okay, I want to have precise control over tissue repair, over bone repair. And bone will only form in the shape of the implant, which is something that physicians have not had until now.
And does it change the behavior of the protein in any way?
No, it doesn't affect what's called the bioactivity or the behavior of the protein. So that's one of the core strengths of the technology is that you preserve the natural function of the protein. You just turn it into a version that's sticky, like a paint.
And are you focusing on growth factors, or are there proteins you might be looking at?
So we, through the company, actually has focused on proteins that are considered growth factors. And because it can be applied to any protein, you can imagine now you can use this as a platform for any tissue that you'd like to repair virtually. So the efforts have been at modifying BMP2 first because that forms bone, but the company is also doing work in cartilage and in soft tissue repair.
Your lead candidate is AMP2, a recombinant protein coating that can promote bone growth. What's the clinical path forward, and how does the FDA treat this? Is it considered a drug, a device, a drug-device combination?
Sure, that's a really interesting question because you're combining a device with a biologic or drug. The FDA has designated the company's first product as a Class 3 device, which is a combination product, but it's regulated through the device division of the FDA. And so that provides certain benefits. They have experience already with how to regulate these types of combination products. They have what I consider a quite good and clear path. The clinical trials you need to do are usually smaller than you would for a drug, and the timelines are shorter. So it offers advantages in that you can get product to patient, get approved product to patient sooner than if it were a drug.
And is there any sense of timing on the clinical development?
Yes. So the work that's going on now at the company has taken it all the way through the late stages of what's called preclinical, so the animal studies and safety studies. And that means that next year, the company will be starting its first in human clinical studies in probably the middle half of next year. So it's coming very quickly.
You mentioned some other applications you're looking at, and one can only imagine the potential for this being considerably broader. But what's the business strategy here? Is this the idea to bring your own products forward, or to partner with device companies that may have applications for this?
Yeah, so that's also another really interesting question because the technology lets you modify existing devices as well. Any device that has or implant that has ceramic or actually mineral content, of calcium phosphate mineral content, can be modified with this approach. So if a company has, let's call it a legacy implant that does okay, and they want to make a next generation regenerative implant, they can use this technology. So there are a lot of opportunities for partnering. But the company itself has also developed its own implants, so it will have its own organically produced combination products as well. So it lends itself to both out licensing and to internal growth.
At this point, have you seen any limits to the types of proteins that can be used as coatings? And are there other therapeutic potentials besides promoting growth and repair that you're considering?
Yeah. So far, the company has looked at about a dozen different proteins in various families. And these are directed at various tissues, and every single one of those has been able to be modified using this approach without affecting its activity. So everything from, let's say, skin repair to neural repair, bone, cartilage. So the universe of proteins that are available to modify with this method and to implant in a precise way is almost limitless. You could also imagine, and we have explored the idea of using this for local delivery for cancer treatment, for example, in glioblastoma, where you have wafers that are placed near the tumor site. So those applications are also available. Just as a company, it's had to focus on tissue repair, but these other areas are of great potential.
Lou Alvarez, founder of Theradaptive. Lou, thanks so much for your time today.
Thank you, Dan.
Thanks for listening. The Bio Report is a production of the Levine Media Group. To automatically download this podcast each week, subscribe to our RSS feed or through iTunes or other podcast manager. To join our mailing list, go to levinemediagroup.com. We'd love to hear from you. If you want to drop us a line or are interested in sponsoring this podcast, send an email to danny@levinemediagroup.com. Special thanks to Jonah Levine, who composed our theme music, and the Jonah Levine Collective, which performs it.